Hello and welcome to our presentation about how to build digital load cells with PICOSTRAIN conveniently. My name is Ralf Emberger. Together with my colleague Zhu Dengke, I will hold this presentation today.
您好，欢迎参加我们的研讨会。今天我们演讲的题目是如何通过 PICOSTRAIN 测量原理轻松实现数字传感器。我的名字叫朱登科，我和我的同事 Ralf Emberger 先生将会给您做今天的演讲。
First of all, some words about acam-messelectronic. Acam is a fabless vendor of integrated circuits in the field of electronic measuring equipment.
首先来介绍一下德国 acam 公司。acam 公司是一个无晶圆生产的集成电路设计公司，它的主要应用领域是在电子测量设备上面。
We have 4 product lines for various type of sensors, mainly CMOS chips with time-to-digital converters as a measurement core.
我们一共有4条生产线，针对不同应用的传感器电路，那么主要是以 CMOS 的时间数字转换器为测量的核心。
acam is located in the southern part of Germany, close to Karlsruhe, and was founded in 1996.
那么德国 acam 公司是位于德国的西南部，在 Stutensee 这个城市。那么成立的时间是1996年。
Our distributor in China is Secom Telecom. It's located in Shenzhen, but has offices all over China, and is a powerful partner therefore for us.
那么我们在中国有一个强大的代理世强电讯有限公司，他们的总部在深圳，另外他们在全中国各地都有办事处。
The PICOSTRAIN product line provides innovative electronics for strain gauge sensors with high precision and low current consumption.
PICOSTRAIN 为应变电阻测量提供了非常革新的测量电路，高精度和低功耗测量是它的主要优势。
It was introduced in 2002 and is now in the 4th generation. The latest product is PS081, a single-chip solution consisting of a microcontroller, converter, and LCD driver.
那么2002年第一个产品开始到现在已经有4代产品了。最新一代产品 PS081 单芯片测量方案，它包括了单片机、转换器和 LCD 驱动在一身。
Some PICOSTRAIN milestones are listed on this slide, where 2002, the first generation of PICOSTRAIN was introduced with PS081.
那么我们来看一下 PICOSTRAIN 的一些里程碑的事件。那么在2002年 PICOSTRAIN 的第一代芯片被设计出来。
In 2004, we won the Innovations Award for PS02 for our innovative measurement principle at the ISWM, an American trade show for weighing scales.
那么在2004年的时候 PS02 这颗芯片在美国的 ISWM 展会上获得了最佳革新技术奖。
In 2007, we introduced the first generation of PICOSTRAIN as a single-chip solution. With 2009 and PS081, we then launched the enhanced version of PS08.
在2007年的时候 PICOSTRAIN 的第4代产品 PS08 恒气单芯片测量方案被推出。那么在2009年我们又推出了 PS081 PS08 的增强版芯片。
There are manifold applications for PICOSTRAIN, such as solar scales, for example, solar body, solar kitchen, or hanging scales, but also high-resolution industrial scales, low power scales, and digital load cells, where we want to focus on today.
那么针对我们这种测量原理，实际上有很多种应用可以做，比如说太阳能方面的应用，太阳能人体秤、太阳能厨房秤等。另外还有一些低功耗、高精度方面的应用，比如像工业恒气、数字传感器等等。那么今天我们将会给您介绍数字传感器方面的应用。
So how is the situation of digital load cells today? First of all, in the last decades, the digital load cell was a niche product. This is mainly because the production and the adjustment is very elaborate and expensive.
那我们来看一下现今数字传感器的情况。在过去的10年当中，数字传感器还是一个比较特殊的概念性的产品。那么主要由于它的独特的生产和工艺，另外以及它的高昂的价格。
This is the reason why its counterpart, the analog load cell, is still a state-of-the-art today. And this is mainly because the production is very well known and practicable of analog load cells. However, digital load cells are used in some areas, for example, where long cables are used and you don't want to lose signal strength, where there's one single processor combined with various load cells, or where there's a need for good EMI protection or fast replacement of the load cell as a whole unit.
这也是为什么现在这个模拟的传感器是一个主要趋势的原因。那么因为模拟的传感器它的这个生产工艺都是大家众所周知的，而且价格也便宜。那么尽管如此呢，数字传感器还会在以下一些方面进行使用，比如说当需要导线比较长的时候，而且不能损失信号强度的情况。另外呢，比如说需要一颗单片机或者一个主机连接多个传感器测试的时候，另外还有在这个 EMI 干扰较大的时候，需要被大大降低的情况下，那么还需要比较快速准确的来更换传感器的情况下。
For example, the digital load cells are applied in truck scales or in electromagnetically noisy environments.
那么比如说这个数字传感器可以应用在汽车横当中，在这个汽车横当中，这个电磁干扰是非常强的。
So today's challenges are listed on this slide. The production of DLCs is very elaborate and costly today. The main reasons for that are that the mounting and assembling cannot be combined very conveniently because the load cell needs a lot of special adjustment by hand for gain and offset, and this needs to be done separately, and later on there's added the electronics.
那我们来看一下现今建立数字传感器的一些挑战。因为建立数字传感器是非常昂贵和复杂的一件事情，那么主要的原因有下面几个。安装和装配这个传感器和电路需要分开进行，它们不能非常方便的进行结合。另外，传感器的标定是非常复杂，而且需要很多时间。另外，对于传感器的温度增益和零点的补偿，需要花很大的功夫。
So there are very high efforts needed for doing the temperature compensation for gain and offset drift, and this is not easier than doing it with the analog load cell. There's a lot of manual trimming of the load cell's adjustment resistor, and it's very difficult to meet legal specification like OML 6000. So there are a lot of efforts needed to do that and a lot of time needed to do that.
那么尤其对于这个传感器的温度补偿来说，相比较这个调整模拟传感器的温度特性，数字传感器的温度特性调整要更加难，很难达到比如说 OIM 6000的这种标准。另外呢，需要很长的时间以及很多的手工工作，手工的机械调整和传感器的补偿也就意味着需要花大量的人力和物力。
There's very little space for automation, costs cannot be lowered, and therefore the demand for DLCs is still moderate due to high prices.
那么对于整个数字传感器的生产，实际上自动化是很难实现的，所以在现今数字传感器还并不是非常适用。
So how does PICOSTRAIN make the production easier? This is mainly achieved by simplifying the production workflow. Therefore, we have 2 points which simplify it. First of all, the convenient temperature compensation of PICOSTRAIN by the integrated microcontroller without the need of further adjustment resistors. This leads to an easier mounting and assembling, where the electronics together with the load cell can be mounted first and then temperature compensated.
那么我们来看一下 PICOSTRAIN 如何来使生产更加容易。那么 PICOSTRAIN 简化了整个生产流程，主要通过以下2个方面。首先，通过它的内部集成的单片机，很方便的对于温度、增益和零点进行补偿，无需任何其他调整电阻。那么这个使这个生产过程呢简化成为2步安装和装配。那么首先可以将这个传感器和这个电路部分放在一起，完全装配好。之后第2步呢，再通过温度补偿进行调整。
As illustrated on the slide, you can see a two-step approach, where in the first step you first mount the complete cell with the electronics together, and then in the second step there's the gain and offset adjustment without manual trimming. So there's room for automation, and you can make a convenient temperature compensation for the wholly mounted cell.
那么您可以看见在这个图上有2步可以做。那么首先呢是将这个电路完全装在传感器之内。那么第2步无需人工机械调整，而是软件将温度、增益和零点进行补偿。那么这将会简化整个这个传感器的生产过程。
So if we compare the production of today and how it could be tomorrow, we can see that today the calibration of the load cell is very elaborate and the electronics is mounted afterwards. So automation is hardly possible.
那么我们来比较一下现阶段如何标定这个数字传感器，另外今后如何应用 PICOSTRAIN 来进行方便的生产。那么首先今天的现状是这样，那传感器的标定步骤是非常复杂的，另外呢电路部分需要之后才能安装，这样的话导致自动化的生产很难进行。
With PICOSTRAIN, there's the advantage that you can assemble the whole cell with the electronics first and then make the temperature compensation afterwards, which is done by the integrated microcontroller and therefore doesn't need any mechanical trimming. So the automation is possible and therefore you get a simpler workflow and a simpler production.
那么应用 PICOSTRAIN 测量原理之后呢，我们简化了这个生产的流程。电路部分首先可以直接装配到传感器之内，另外呢，不需要机械调整传感器的补偿电阻，用单片机内部的软件调整就可以进行。另外，可以通过这个自动化的生产来进行校准，使生产更加简单、更加容易。
So how does the temperature compensation work at PICOSTRAIN? Of course, I cannot explain this very detailed in the short presentation, but nevertheless, I want to give you a short overview about how it works.
那么我们来看一下 PICOSTRAIN 如何简化这个温度的补偿。那么当然，我们希望将所有的细节部分都告诉您，但是呢，由于时间的原因，我们没有办法全部告诉您。不过今天我们可以给您大概讲一讲，我们如何来通过 PICOSTRAIN 进行补偿。
First of all, we only need one R-span resistor in the bridge and no further adjustment resistors.
那么首先呢，我们仅需要一个 R-span 补偿电阻，不需要其他的温补电阻。
So you see here the typical PICOSTRAIN bridge with 4 strain gauges, and here in green there's the R-span. The other resistor here drawn with the dotted line is only a virtual resistor, that means it's only existent in software.
那么您可以看到这个图中是一个4个应变电阻组成的一个桥接，另外呢还有一个绿色的 R-span 温度的补偿调整电阻。那么在这个虚线所画出的这个电阻是实际上是由软件虚拟出来的零点补偿电阻。
In the PICOSTRAIN measurement principle, we have discharging cycles where the load from the capacitance is discharged over the strain gauges sequentially, and therefore we can determine the size of our span as indicated by this small picture here, as our span is in one part of the half bridge but not in the other one.
那么您可以通过这个图可以看到，实际上我们这个测量都是通过这个电容进行放电测量的放电时间。那么这个应变电阻分别通过这个电容进行放电，我们记录这个放电时间，然后进行比率的测量。通过这种方法，您可以看这个图，那么我们就可以确定 R-span 电阻的大小，因为我们是只有一个半桥通过 R-span 电阻进行放电，另一个半桥是没有 R-span 电阻。
The ratio of the discharging times equals the ratio of the resistors, indicated by the small pictures above here.
那么补偿电阻它的这个比率实际上就相当于我们测量出的这个时间的比率，您可以看到这个图上的显示。
Having a look at the equation here on the bottom, you can see the strain gauge resistors ratio is expressed here, and we also have the influence of our span, which is then corrected by 2 factors called TK offset and TK gain. These are 2 register settings within the PS081 microcontroller, and so it is a compensation by software.
那么通过在图中的这个数学方程式呢，您可以看到我们是如何加这个 TK offset 和 TK gain 的这样一个系数。实际上我们是将这个 TK offset 这个系数加在这个传感器的比率的这个值当中，另外呢将这个 TK gain 的系数乘在这个传感器的补偿电阻这个公式当中。那通过这种方法呢，我们就可以来补偿温度的这个零点和增益偏移。
You can easily see that by those two factors we can influence the overall results. For a detailed description of our span and the TK gain, TK offset compensation, we wrote a dedicated white paper which will also be available on our booth.
那么您可以看到，通过这种TK gain 和 TK offset 系数的方式呢，我们可以来改变这个整个传感器的温度特性。那么对于这个 TK gain 和 TK offset 的补偿的一些细节的东西，您可以到我们展台上拿这个技术白皮书，也就是温度补偿方面的技术白皮书。
So what are the advantages by building a digital load cell with PICOSTRAIN technology?
那么我们来看一下，通过 PICOSTRAIN 测量原理来如何体现这个建立数字传感器方面的优势。
As we outlined already, the production gets simpler and you can save costs.
那么我们已经知道了这个 PICOSTRAIN 测量原理可以简化生产，另外可以节省成本。
This is thanks to the more efficient workflow. But on the other hand, you also have a smaller PCB size and a reduced number of components. That means the bill of material is fairly short.
那么主要是由于它可以更有效地使生产进行，另外呢，减少了元器件的数量，缩减了这个元件的成本，还缩减了这个 PCB 的这个尺寸。
Because there's no manual adjustment needed, there's higher automation possible. This leads to less labor cost and to saving production time.
那么因为它减少了这个校准传感器所需要的时间和工作，另外呢，所以它减少了这个手工补偿的这个时间和工作。那么另外它可以通过不同的工作流程，还可以再节省生产的时间。
You can increase quality and reliability without additional expenses, therefore. So, in other words, you make the adjustment procedure for the OML 3000 scale, but you get the quality of a OML 6000 scale in regards of temperature compensation.
很重要的一个方面就是在不增加成本的情况下，它还可以提高整个产品的质量和可靠性。比如说，通过建立这个 OIML 3000标准的传感器，则可以实现 OIML 6000的性能，这是非常好的方面。
The second advantage is the convenient temperature compensation with PICOSTRAIN. You can wholly mount the unit first, that means putting the electronics into the load cell and then do the temperature compensation.
那么第二个主要优点就是简单的温度补偿。那么你可以首先将电路放进传感器身体，然后进行一次到位的补偿。
As there's no mechanical trimming needed, there are faster throughput times and normally no iterations in adjustment procedure needed.
那么由于不需要手动的机械调整，那么节约了补偿的时间，另外不需要再进行重复的校准。
In other words, there's automation possible and the workflow gets simpler.
那么通过这种方式呢，自动化的生产流程可以实现，那么整个流程被简化了。
This way, the PICOSTRAIN temperature compensation makes the calibration easier.
那么通过这种方法呢，数字传感器可以完全满足标定的要求，而且更容易更换。
A further advantage is the low current consumption, as it is required, for example, by battery-driven DLCs or wireless DLCs or portable DLCs, which is possible thanks to the PICOSTRAIN measurement principle.
那么另一个非常主要的优点就是测量的低功耗。那么低功耗在一些特定的场合也是非常必要的，比如说电池驱动的数字传感器、无线方式的数字传感器以及便携式的数字传感器。
The pulse measurement principle of PICOSTRAIN does only consume current when needed for the measurement. There's no steady current in the bridge and therefore the overall current gets very low.
那么由于这种脉冲式的测量原理，那么整个测量的功耗是非常低的，仅在这个测量的时候才会产生功耗，不测量的时候则不会有功耗的消耗。那么所以 PICOSTRAIN 的整体测量功耗是相当低的。
In the table on this slide, you can see typical current consumption with PICOSTRAIN. This includes the current through the strain gauges, so that's the total current consumption.
那么在这一页的表格当中，您可以看到在不同分度情况下的一个功耗方式。那么你可以看到的这个功耗是包括传感器在内的整体功耗。
For example, a 3000 OIML division scale can be realized with 180 microamps. If we want full performance of 200,000 stable scale divisions, then we would need in the range of 4.5 milliamps.
那么你可以看到，在这个表格当中，举个例子，我们要实现3000 OIML 分度的情况下，我们仅需要180微安的这个功耗。另外，当你需要达到最好的这个测量分度的情况，比如说20万分度的情况下，那么你需要的功耗仅为 4.5 毫安。
Compared with classical AD converter solutions, this is a very low current consumption when you consider that normally the converter itself needs approximately between 1 and 2 milliamps, and we have this current for the whole system with almost highest performance.
那么相比较这个普通的数模传感器、数模转换器来说呢，实际上我们的功耗是非常低的，因为数模转换器它芯片本身可能就要需要几个毫安的这样的测量功耗，而我们在最大测量性能的情况下，仅需要几个毫安，是包括传感器在内的。
Another beneficial consequence of the low current consumption is that there's almost no self-heating. It can be reduced significantly so that there's no zero drift in the first minutes when you switch on the scale.
那么非常感谢这种脉冲式的测量方式，使传感器本身的自热现象也大大降低了。那么通过这种测量方式呢，在开始的一段时间内，零点偏移是非常小的，甚至是没有的。
Another advantage is the use of DLCs in standard scales. Although not very commonly used nowadays, we think there's a number of advantages with this approach.
那么另一个优势呢，就是将数字传感器用于标准的衡器当中。尽管现在数字传感器没有很广泛的应用于标准衡器，但是我们相信数字传感器会给标准衡器带来很多优势。
The basic idea of this approach is to split up the design in an analog part and a digital part.
那么这个带来的主要优点是我们将这个整体的标准衡器呢分为数字部分和模拟部分两部分。
This way there's several advantages. For example, that you can adapt the PCB especially to its purpose in a digital sense or analog sense and make it more effective therefore.
那么这样的话我们会带来一些优点，比如说我们建立 PCB 的时候可以针对数字部分建立和针对模拟部分建立，那么使这个工作更加简单。
You can also reuse the PCB in many type of scales. For example, take the weighing unit and just design it into another scale. So it's a very modular and flexible system.
那么另一个优势呢，就是说你可以将这个数字传感器的电路在其他的这个标准衡器中进行应用，你不需要进行再设计，你只要把它拿出来放到其他的这个标准衡器当中就可以。
It also allows you to set up an analog design group and a digital design group where expertise and knowledge can be specialized for the purpose. And this way, development work can be divided efficiently.
那么另外你可以将这个研发工作分开进行，比如说你把它分开为模拟部分和数字部分，这两部分可以没有任何相干，那么研发的也比较简单。
Due to the fact that the weighing unit, the digital load cell, is very good encapsulated, you can also expect much less EMI problems.
那么由于这个数字传感器它的电路部分实际上已经是安装在这个传感器壳体内部，由于它的屏蔽性能非常好，所以呢它可以大大降低这个电磁干扰的影响。
So in conclusion, we saw that building a digital load cell with PICOSTRAIN has several technical and commercial advantages.
那么作为总结呢，我们可以看到通过 PICOSTRAIN 建立数字传感器可以在技术和商业上都获得很多益处。
It enables you to produce high-quality digital load cells with moderate efforts and costs.
那么它可以通过较小的努力就可以建立高质量低成本的数字传感器。
Let's come from theory to practice now when we talk about the DLC prototypes which we built up at ACAM in the first quarter of 2010 to prove that a concept like we imagined it was feasible and to get first results.
那么我们来看一下我们建立的数字传感器的实际原型。那么2010年的第一季度呢，我们公司建立了几颗这个数字传感器的原型。那主要目的是在于调查和研究是否所建立的这些数字传感器在一些精度、温度以及功耗方面可以获得我们所预期的效果。
The goal was to investigate if the setup was possible and also to get first results of resolution, temperature behavior, and current consumption.
那么如刚才我所说的，主要目的还是在于看看是否所建立这些传感器可以在这个精度、温度以及功耗方面都可以达到我们所预期的这个效果。
For this purpose, we took a standard C3 load cell and asked our load cell manufacturer to mill out an area for the PCB.
那么针对这个目的呢，我们应用了我们的传感器供应商提供的 C3 的标准传感器，不带任何胶的标准传感器。
In the picture you can see the naked load cell body with only the strain gauges and 1R span applied, and here's the area for the PCB.
那么在这个图中呢，你可以看到这个是一个裸露的传感器，它是带有电阻应变片的。另外呢还有一个2 span 的补偿电阻，还预留了给 PCB 的这一块区域。
The PCB was then put into the milled out area. You see here the mounted PCB in the load cell body.
那么这个 PCB 呢是放在这个已经预留的这个尺寸当中。那么你可以从这个图中看到我们建立的这个很小的 PCB 放在这个孔当中。
The dimensions of the PCB are very small with 22 times 19 millimeters.
那么这个 PCB 的尺寸是相当小的，它只有22乘以19毫米大。
You can see in the second picture here the wiring of the strain gauges, which was done according to the PICOSTRAIN connection.
那么在另一个图中，你可以看到，实际上我们是将这个传感器的连线通过 PICOSTRAIN 的连接方式，那么这样可以满足我们 PICOSTRAIN 测量的要求。
Besides the 1R span, there are no further additional adjustment resistors needed.
那么除了仅用了一个2 span 补偿电阻之外呢，不需要其他的任何补偿电阻。
In the end, we put a silicon glue on top of the wiring of the strain gauges. There's one transparent type for demonstration on our booth. The other prototypes were filled with a non-transparent glue.
那么最后呢，我们将这个胶盖在这个电路部分上。实际上我们有两种不同的胶，一个是透明的胶，另外一种呢是白色不透明的胶。您可以在我们的这个展台上可以看到这两种不同的胶。
The good news is that building up the prototypes was successful, and we could prove that the concept how we imagined it was feasible.
那么实际上我们建立的这个数字传感器的原型是非常成功的，另外它验证了我们之前的想法是完全可行的。
We also did some first investigations, and I want to present you the first results of that.
那么我们同时呢也做了一些实验，那么我们将会给您看一下我们进行实验的一些结果。
On this slide, you see the noise behavior of the DLC prototype, where we configured 2000 stable scale divisions, that means peak to peak. Here in the noise diagram, you see one division out of these 200,000.
那么您可以看到我们现在呢这个是一个测量噪声的曲线。那么您可以看到这个图中，我们实际上配置的是满足20万稳定显示分度的这么样一个测量。您可以看到这个虚线所代表的是一个测量分度20万分之一。
So you can see that we almost reached the 200K stable division, which is much more than it would be needed for OML 3000 or OML 6000.
那么您可以看到，实际上我们是几乎满足了20万分之一的测量。那么这个对于 OIML 3000或者 OIML 6000的测量来说是完全没有问题的。
It corresponds to almost 1 million effective divisions internally.
那么这个20万的稳定显示分度呢，相当于几乎100万的内部有效内码。
The stabilization time, which can be configured as the resolution in PICOSTRAIN, was here 0.7 seconds.
那么在这个情况下，我们配置的它的稳定时间是 0.7 秒。当然，您可以在我们 PICOSTRAIN 内部进行灵活的调整。
We think, based on the fact that we're talking about a standard C3 load cell built to a DLC prototype and a supply voltage of 3.6 volt, this is a very nice result.
那么根据我们这个应用的这种标准的 C3 的数字传感器以及供电电压为 3.6 伏的情况来说，那这样的一个测量性能我们是非常满意的。
In the second step, we did the temperature compensation according to the PICOSTRAIN principle and determined the gain and offset drift factors. So we also show you some results here.
那么之后呢，我们对这个数字传感器的原型又进行了一些温度上面的测试。另外，我们确定了相应的这个增益和零点的偏移补偿系数。
The diagram on this slide shows the gain drift after adjustment with PICOSTRAIN method.
那么在这个图上面呢，我们给您演示了，就是在我们进行增益补偿之后，我们的数字传感器的一个温度增益方面的情况。
You see in the diagram here two red lines which are indicating the limits for OML 6000.
那么这个在图中的这个红线的区域呢，实际上是OIML 6000所规定的一个范围。
And the gain drift is now drawn into this graph at -5 degree, at 10 degrees Celsius, at 25 Celsius degree, and 40 Celsius degree. And you see the curve is deeply within the OML 6000 limit.
那么您可以看到这个蓝色的曲线，实际上我们是从-5度、10度、25度、40度这样来获取的这个测量结果。您可以看到，实际上整个这个增益的测量结果是完全满足 OIML 6000的标准。
The same is true when it comes to the offset drift. We did another measurement and diagram here.
那么对于这个温度的零点偏移来说呢，同样也是非常好的一个测量结果。您可以看到我们图中这个零点偏移的测量结果。
This way we show you the offset drift before and after adjustment.
那么我们在这个图中呢，是给您画出了在零点补偿调整之前和之后的这个一个补偿效果。
So in the graph you see here the orange line showing the offset drift before adjustment, where in the dotted lines there's always a temperature jump, for example here from 40 to -10 or here from -10 to 5 degrees Celsius.
那么您可以看到这个图中的红线是在没有进行零点补偿之前的一个零点的变化。那么您可以看到这个灰色的虚线，实际上就是在从一个温度跳到另一个温度的一个情况。比如说这里是从正的40度到负10度。
So you can easily see that the offset drift is quite high. Here it would be in the range of 35 divisions out of 6,000, compared with the OML 6000 limit, which is indicated again by the two red lines. This is far outside the OML limit.
那么在没有补偿之前呢，您可以看到红线的这个零点的变化是很大的，大概最多是35个这个分度值在OIML 6000当中。那么这个与 OIML 6000的这个标准来相比较的话，是完全不满足它的要求的。
In contrast, the blue line here shows now the offset drift after adjustment. So you can easily see on the first side that the curve is within the OML 6000 limit. Please consider that OML specifies the drift after a settling time of 2 hours, so that means the real drift should be seen from this point to this point, for example, and not the dynamic curve, which is the reaction of the load cell right after temperature jump.
那么您可以看到这个图中的蓝色的线呢，是我们在进行零点补偿之后的这个零点测试的结果。那么您可以看到这个零点测试结果呢是完全满足 OIML6000 标准的。另外想提到的一点就是说OIML 的这个测试的规定呢，它是需要传感器在温度变化之后稳定一个相当长时间的。那么您可以看到在温度进行变化的时候，这一段非常大的跳动实际上是不会被记录下来的。实际上我们的这个零点的这个变化是相当稳定的。
The offset drift behavior of this particular DLC prototype would be good for OML 10,000.
那么通过这个测试呢，我们可以看到这个我们的传感器原型它的零点完全满足 OIML 10000的标准。
Of course, we also measured the current consumption of the DLC prototype, where we want to show you the results on this slide.
那么当然我们对数字传感器的原型也进行了在功耗方面的一些研究，我们会给您在这一部分来进行一些阐述。
Again, due to the pulse measurement principle in PICOSTRAIN, current flows only when the measurement is done and there's no steady current in the bridge.
那么当然通过我们这种脉冲式的测量方式，只有在测量的时候才有电流流过传感器，而其他的时候则没有电流。
The current consumption depends on the configured resolution, so we exemplarily picked some of the interesting resolutions like OML 3000 or OML 6000 and showed this in this table.
那么当然这个电流的消耗是与你的所需要的配置有关系的，因此我们在这里呢列出了一些标准的一些配置，比如说 OIML6000、OIML3000 等这样的配置情况下，电流消耗具体是多少。
You see in the table in the first column the resolution of the stable divisions, the stabilization time and the needed current for that.
那么你可以看到这个表格呢，这个第一列是我们所需要的测量的精度、峰值分度，那么以及我们测量需要的稳定时间，以及相应的这个电流消耗。
So we could confirm that for OML 3000 you need approximately 200 microamps. With 650 microamps you can do a OML 6000 scale, and when you want to do a very low current application, then you can still reach 10,000 divisions with only 70 microamps.
那么您可以看到，实际上我们可以确认，就是如果你需要建立 OIML 3000分度的恒器的时候，你需要的功耗仅为200微安。那么在这个建立6000分度 OIML 的情况下，仅为650微安。如果你需要一些低功耗的应用的时候，比如你建立10000分度的这样的测量精度的时候，你需要的功耗仅为70微安。
The interface of the PS081 and therefore the DLC prototype is SPI. This is a full duplex serial interface bus 4-wire based and is a standard protocol in master-slave applications.
那么我们这个数字传感器原型的这个通信接口是 SPI 串行接口，那么这种接口是4线制的全双工串行接口总线，它的这个标准测量协议主机从机模式可以为这个数字传感器提供很好的这个数据传输方式。
Connections up to 3 meters are no problem, and easy interconnection between DLC and its counterpart, for example microcontroller, is given.
那么这个连线呢，可以长达2到3米都没有问题。另外呢，可以将这个数据传输在单片机和数字传感器之间非常容易的进行。
Therefore, it's perfectly suited for standard scales where you have short cable length and the microcontroller directly close to the digital load cell.
那么这对于这个标准的这个恒器来说，这个线比较短的情况下来说，是非常有益处的。
For other protocols, of course, there are external transceiver chips available.
那么对于其他方式的通信协议呢，比如像 RS232 也可以应用一些通信协议转换的芯片来实现。
To sum up the results with the DLC prototype, we can say that they were built successfully with a new workflow, and first good results were obtained.
那么作为总结呢，我们可以讲这个数字传感器的原型通过这种新的生产流程可以被成功的制造出来。
We had good measurements in the area of noise behavior, temperature adjustment and remaining gain in offset drift, and also low current consumption.
那么经过我们最初的测试呢，在测量噪声、温度调整零点和增益偏移方面呢，功耗方面都有不错的表现。
Our explications, our results and findings, which we had in this presentation also, are all written down in a corresponding white paper for building DLCs, and this white paper is really available on our booth.
那么我们对这个数字传感器原型的一些调查研究，以及我们测试的一些结果，还有相应的一些东西，您都可以在我们的这个技术白皮书中找到。您可以在我们的展台上免费获取我们的技术白皮书。
So please feel free to come to our booth after the presentation and get your personal copy of the white paper.
那么您可以到我们的展台来拿这个技术白皮书，这个我们非常欢迎您到我们展台来拜访。
We want to thank you very much for your attention. Again, it was very nice to have this presentation with you, that you took the time. Please visit us at our booth on B1112 and B2324. We have the copy there of the white paper and also some demonstrations of the DLC prototype and other demonstrations to show you our PICOSTRAIN technology.
那么最后呢，非常感谢您能参加我们这一次研讨会。那么也欢迎您到我们的这个展位上进行拜访。我们的展位是 B011、B012、B023、B024。另外，您到我们展位上呢，除了可以获得这个数字传感器的技术白皮书之外，您还可以看到我们这个数字传感器的原型。我们在展位上有不同的原型可以给您演示。
Again, thank you very much for your attention and goodbye.
非常感谢您的